Thank you everybody for coming for this final session of this series. This work is mostly done together in collaboration with Nicolo Colombo, who's sitting right there. If there are any mistakes in these slides, you can blame me for that, but much of these are his ideas, including some reuse of his past slides. I also thank my collaborators and Soong Kang from the Management Science Department, and part of what I'm going to present is some work that we have already started with Arthur Gretton from the Gatsby unit. So that talk is actually going to be slightly different from what the abstract was, partially because there are things that we didn't finish in time for today as I was planning. So the structure that I'm going to present here is not exactly what was in the abstract, but it's still only within the context of work that we've been doing for a couple of years with data graciously provided to us by Transport for London. So these are general problems in transport systems, but the London Underground is a great motivation, is a great case study that allows us to understand how these things actually perform in practice. So the presentation has two halves. They are not immediately connected. It's part of a bigger project. And these parts haven't been put together yet. But the main two problems I'm talking about, one corresponds to understand some hidden structure in passenger behavior. So you're all familiar with the oyster card here, how it works, how you use it on a daily basis. But lots of information out there about your behavior is not captured by the oyster card. So you want to understand a little bit about your choices, for example, of routes within the underground and how this influences your travel time. So the first half is going to be about that. And this is already published work that was out last year at the NIPS conference, 2017. So the second half is work in progress. And this, as I mentioned, is going to be much more theoretical than I wanted to present here. So there will be about methodological ideas for understanding shock modeling. There is some unplanned disruption in the tube. People behave in some maybe unusual ways. And you want, after observing several of these disruptions, to understand whether there is a common pattern behind that. So you want to understand if a new disruption takes place, or if you want to simulate what might happen when a disruption takes place, what people will do. So again, measure in terms of what you can observe with the oyster card. Okay? So this is this first half. I'm going to explain the basics of this problem. I'm going to put it in the context of experiments done with the London Underground. So in one sense, this fits within a bigger picture of complex systems. So if you think of engineered systems, they have many parts. These parts interact. There are several ways of describing interactions. Networks are a common way of representing these. And of course, a network structure follows immediately from what we observe from the London Underground. So if you imagine stations as nodes and the links between them as edges in a graph, the underground naturally can be represented and understood as a network. Now, the data that you observe there is data that involves human activity, in this case, passenger behavior. So there is some sort of interaction between the spatial topology of the system that you have and users' choices, users' behavior. And when I talk about behavior here, I'm not talking about idealized agents that are extremely rational, they know exactly what to do with the information they get. Is what really aiming here is to understand actual people's behavior, not an idealized agent, but what people actually do when using a system like the underground. Okay, of course, you cannot just, it's not productive to ignore that people are not completely rational. Most of the time, they do something sensible. And you're going to exploit some assumptions about plausible choices that people might make as a way of simplifying a problem in achieving more realistic results. So tomography in this case here is a classic problem by now in engineering and statistics. So you have all this network structure data. You may observe some partial measurements in it. So if you think of the oyster card, you know where you tap in, you know where you tap out. You don't observe the trajectory in between. So the name tomography actually comes from is directly inspired by the medical literature. So you have some sort of surface impressions. There's some structure underneath the surface impressions. You want to understand the inner structure of a system. Okay, so in our case here, it's going to boil down to latent choices, unobserved choices of trajectories. And as you may know, Transport for London in particular has newer technology that uses your mobile phone signal to get a more precise understanding of which trajectories you choose. So what I'm going to present here, in one sense, is a complement to what you can get with more refined signals, such as mobile phone technology. So mobile phone technology, of course, provides way more information than what Oyster card can give to you. But the goal here is casting a more general problem of network tomography using the London Underground as motivation. And from a practical viewpoint, it's going to provide a complementary set of analysis to understand trajectory modeling and how people choose different paths according to the time of the day. So I'm not saying here that this is going to be a main state of the art from now on to understand trajectories. Is one component of different ways by which transport authorities can use to get a fuller picture, because even mobile phone technology doesn't give you full coverage what's going on in a system. Okay, so this is one asterisk I wanted to add it before somebody asks what are one recent technologies of understanding these trajectories of passengers. Okay. So the way I understand a trajectory here is really in this discrete time, discrete space structure. So the discrete space is given by this interpretation of the underground as a network. So you have nodes and vertices. And if you have technology like the Oyster card, even there has a time resolution that is not continuous time. So you actually employ the time resolution of the Oyster card, which is by minute. So if you have something from about 5 a.m. until the end of the day, you have about 1,200 minutes there. You can treat these as discrete time indices of activity. And in the Oyster card data, you do observe origin destination counts. And everything that I'm going to mention here is for systems which do have origin destination measurements. Not everything is like that. If you're familiar, for example, in New York City, there you only tap in or you only put information when you enter, not when you go out. So these methods are not really appropriate for data that doesn't have also the destination of individual passengers. Now, if you think about tomography in general, there are different variations of this problem. So you can use this to get other properties, other understanding of particular features of the system. I'm going to explain also here one application on estimating load links. So how much traffic is passing through each link at different times of the day.
Quick question, do you have origin destination timings?
Yes, I'm going to show it's a good question that goes with a slide I'm showing later on. Okay. Yes, so one way that this behavior and trajectories are intertwined is when you link this to information such as time. So you may think it takes time to process a navigation task. So each stage of a navigation task, you might have a delay. So you want to understand how much time you're spending in each link within your trajectory, which is also not observed. So in general, you may observe the length of the total trajectory. I'd like to divide it into what happens into each subcomponent, partially related to this thing I just mentioned that you may want to know about how busy particular links are at any time of the day. So in many of these cases, it's a type of the convolution problem. You may observe totals. In this case of delay, you may observe total global times that you take to perform a trajectory, a journey. And you do have the local times at each location in the network. In here, we're going to have, it's given to you a predefined matrix of different trajectories corresponding to possible choices taken by users. So you can imagine matrix A, where somebody did the job of pre-selecting possible paths. Within these possible paths, you can code as a binary matrix. So this will reveal that the structure of this problem is linear in that sense. You can think about adding up the individual times where y is observed and x is not observed if you don't know the trajectory. Okay. So this can apply to different types of problems. The problem that I mentioned to you is a problem that the way I formulated the problem in the previous slide is something that was very classic already in communication networks. Like there are people interested, there are bottlenecks in communication networks. How much time does a packet of information takes to reach from one computer to another computer? So you're interested in understanding where your bottlenecks might be. And of course, when you abstract things away, this applies as well to something like a transport network. And the abstraction, in one sense, just assumes that your raw data has this format. You have the origin, destination locations, and the timestamps of the start and the end of your trajectory. Okay? And out of this, then you get from some sort of statistical inference method, the local delays at different locations, and those loads and path preferences I mentioned here. Okay? Some computational challenges here. Much of the classical literature on network tomography, they assume some sort of special structure. If you have a communication network, for example, some sort of tree structure on how the different ramifications of trajectory choices can take place. You may assume that between any origin and destination, there is one single obvious path. You may assume that the randomness on the delays taken in each location might be independent across different locations. And many of the classical problems, or many of the methods that you see in the literature, in the engineering and statistical literature, may be applicable only to small-scale problems. Of course, there's a whole range of methods out there. Many of the methods that exploit probabilistic information tend not to scale up too well for bigger problems. Now, what we're going to hear to simplify the computational problem modeling this is us making some assumptions. One assumption is that passengers are independent, which we may imagine is not quite true. People travel in groups. They need to be synchronized by the trains which are available to them. So it's not properly true that these passengers move independently, but for the sake of getting a good approximation, that's what we're going to assume here. Okay? As I mentioned to you, the common practice in network tomography is pre-assume that you have a kind of dictionary of plausible paths. So if I give you any 2 points in the underground, you may have an extremely large number of possible paths. You're going to have the working assumption that you have very few plausible paths that you are going to assign as alternatives for users. So there's another cutting that we do in order to make these approaches scale up to something such as dealing with millions of passengers for oyster card data. Okay? And also one assumption that is slightly less realistic is how the journeys which are chosen there independent of the starting time. This could be relaxed. This is a stronger assumption, I would say, because of course, depending on the time of the day, your choice of destination might vary. So this is not something that is hard to deal with, but for the sake of keeping the method simple, that's one of the assumptions you're going to adopt here. Okay? So to give certain defined granular details here. So you can think each of these phenomena is taken probabilistic form. So you may think there's a choice of path, and this choice is probabilistic, and then you need to assign a probability for each one of them. And the idea is try to make the model as simple as possible, not to overload it with too many parameters. And this is a type of model structure that we assume here, which is going to do well for our purposes. So in a nutshell, if you think about the choice of paths, you may think once you select plausible paths for any origin destination, within this space of plausible paths, I'm representing this matrix here as all the plausible paths between a particular origin O and a particular destination D, is this going to be proportional to some features of the path. So here I'm placing this in a very abstract framework, but in our actual experiments, this is going to boil down to things such as statistics of the complexity of the path. Number of hops is one statistic. Number of changes between different lines is another statistic. So you combine them with some free parameters. I'm representing here one free parameter beta. So these free parameters are then going to be fit by some statistical method. But the space of possible probability distributions of paths is expressed in that way. Now, when you think about how it relates to the time of travel given a particular path, you can think that each path you have some random time that you spend in each link. So you can represent this as random variables too. These are going to be my delay variables that I'm representing as RK. They are the time taken at a particular link K. And there are different probabilistic methods, probabilistic families you could use for this. I'm going to use a very crude choice of family here for the sake of making things computationally simple. So here, as I told you, you assume a discrete time. So you can think about the time spent in each link in terms of minutes. So you have here at each time taken, each link follows a plus some random variable, which we know is a false assumption. Of course, when you think about time taken each link, you'd think there's a minimum threshold and then some geometric decay, for example. But for the purposes of looking what happens when you aggregate them to sum up to the final time taken, this turns out not to be a bad model. So in terms of the observables, it explained the observables well enough. And it has nice computational properties that we're going to see. And when you actually experiment with synthetic data, it does do a good job of getting some decent estimates of what happens within each link. But we know this is not a great assumption for modeling time within each link. Okay? So the observables in this case are actually the origin destination and at the time, the total time taken by the user. So this is going to be our main signal to understand which choice of path you did. So you think of this as a mixture model. There are possible choice of paths. Given one path, this is how the total travel time should be by adding up these random delays in each link. Some of them are going to be more probable than others, depending on the configuration of parameters. So essentially do something akin to maximum likelihood. Try to explain probabilistic observations he had by looking at the aggregates and looking at the possible ways these aggregates can come from these latent delay variables within each link and the latent path choices within each origin destination pair. So you can set up a likelihood function where you turn, excuse me, you're going to optimize particular parameters. So we have this particularly complicated function which I'm hiding behind here. This function A basically tells you the rate of the Poisson at different links. So here this is going to parameterize the distribution of my link, my delay variables R. The way this is done is in a very general sense. So here what we're trying to capture is these rates of these random variables of delays may change over the day, or different periods of the day. So you can have a very flexible function where these rates change during the course of the day, maybe in a periodic way because trains might be periodic in particular lines. So this is going to tell me at a particular minute what is the rate that controls the variability of my delay. And this actually complicates my life because if I'm that flexible in a way that allows this rate to change over time, then this will require knowing how much time has passed in the past. That in particular time, I look at the time I started, I look how much time I've spent so far, and by knowing how much time I spent so far, this will tell me what the rate of delay should be at that particular location, at a particular time of the day. And this will complicate my life because I don't know what these delays were to begin with. So these random delays add up and depend on each other in a complicated way. Even if by the end of the day, I just observe the total aggregate at the end. Okay, but these delays are shared by different paths. This is how we get information to identify what they are. The same link is present in many different origin destination pairs. This allows us to disentangle from these numbers what they are at different locations. But unfortunately, this likelihood function, because of this flexibility, is very hard to compute. So you cannot do this tractably. You may think in ways of approximating that. So here we discuss two approaches. One approach is actually modify the model to be simpler. So instead of having this stochastic dependence, this delay here depending on the delay there, which make this entanglement very hard to deal computationally, we're going to make some replacements on this function that decides on the rate of delay at each time. So here is similar to what I had before. So instead of having the stochastic dependence between the delays, you're going to have just a deterministic number indicating an average time within each link and within each time of the day. So this is just defined recursively. So at each stage k of my journey, I'm going to add up what this median, what this average number was in the previous stage with my average function a. So the difference is this is not stochastic anymore. This is not a dependency among the different random delays. This is just a number that makes all the delays independent and using an average constant for each location in place of the original random delays. So this decouples everything, even though it might be a less realistic model. It makes the computation much simpler. So a second approach is don't change the model, keep it as it was before by using approximation for the likelihood function. So here's something called a variation approximation, which I'm not going to get into details, but basically assumes that when you're actually doing the computation, you try to work with the original model, but approximate it with what would be the closest simple model of independent delays that reproduces the exact model that you started with. So I'm not going to get into details here, but it does provide to you a different way of thinking. So instead of having an approximate model of exact inference, this is an approximate inference from an exact model, the model that motivated things to begin with. And also because you're curious on how much level of detail you actually need for a real system like the underground, because maybe this model that you have as an overkill, yet turns out to be something along those lines. A simpler model actually does as well as a more complicated model. Now, in terms of computation, I'm not going to walk through this. As I mentioned to you, this is a more methodological talk than what was originally planning. But you can call in standard. This may be a hard-to-code model. So if you're actually software engineering for a company that implements a model like this, it might take some effort to code it. But it turns out many of these computations are things that people are already using in standard machine learning methods like neural networks. You have this dependency over time that couples things, but you can express that in a neat way that the computation can be done recursively and can call some standard machinery for doing this computation to you. There are methods that can do some automatic differentiation. But even if you try to code things from scratch or explain more detail in our own paper, it's complicated, not too enormously complicated to understand how to fit this model, even though this is time series dependence that you have there. Okay, so it's just to keep in the back of your mind one practical aspect that coding this in principle may be a bit complicated, but there is machinery that's similar to what you do in neural networks to actually put algorithms that fit these models to work neatly with pre-existing software. Okay? So what I'd like to do to end this section is just show a small experiment. An experiment that uses some synthetic data and then uses some real data provided to us by TFL. The synthetic data, you do know what the ground truth is because you simulate it. So it allows you to understand where they're reproducing those unknowns which are not directly observed if you use the real data. So the synthetic data allows us to control whether they're doing something sensible or not. So the real data is data from TFL, pseudonymized Oyster card data, for one particular day. You're restricting things to zone 1 and 2 for the purpose of illustration, but it could be extended to the entire tube if desired so. I think it had how many transactions here? I think that day was 4 million transactions, but how many were for zone 1 and 2?
Yes. How many?
Yeah.
Around 1 million?
1 million. So I had about 1 million transactions to fit this model for that particular day. So these are some displays on how we reconstruct from the synthetic data path choice probabilities. So because it's synthetic, we design what these are, so we know whether we reconstruct them correctly or not. So what we have here, there's two approaches I mentioned to you, the exact method in a simplified model, the approximate method in the more complicated model. And this display that you have there compares their ability to reconstruct these path probabilities against a very simple baseline. So each number that you probably cannot read at all in this axis is a measure of distance between the truth and the estimated probabilities, so closer to 0 the best. The y-axis, the vertical axis, is what the methods do, and the x-axis is a dumb baseline which just returns uniform probabilities over the paths that you pre-selected. Okay, and the take-home message here is if it's way below this diagonal line, then this is doing much better than a dumb uniform probability choice. And actually, it's very closer already to the origins. The errors actually turned out not to be too bad, especially, surprisingly, I think, that the variation inference method here actually did particularly well in this task. So it was behaving particularly well in estimating these path choice probabilities. Okay, so this is just showing the optimization procedure, because we have all these parameters to tweak. It is just showing how it converges over time. The take-home message in that case is that the variation inference method actually takes longer to converge, but for this task, it does better. So the second task that we have here of synthetic data sets is actually estimating that complicated function that says at each time of the day what's the parameter that regulates my delay distribution. So this is synthetic and probably more complicated than it needs to be. So this is time of the day from 5 a.m. to 1 a.m. the next day. So in this axis here is the rate by which the delays are generated. So the highest, the bigger the delays will be at a particular location. So these kind of periodic shapes that you see there it's just a way of reflecting that because of the ways that trains are scheduled, should observe some sort of periodicity. Well, I'm not claiming here this is realistic, that periodicity probably should be a much higher frequency, given the time resolution you see there. It's just a way of demonstrating that you can reconstruct that by just observing the total travel times of a sample of 1 million passengers. So hopefully it's particularly visible from the back. So you have the truth, the one that you simulate as being the green line, and the reconstructions being the other lines. So I would say it's roughly a very nice fit to what you have there from these different methods in reconstructing these not trivial ways by which the travel delays were simulated at each instant of the day. Now, what you see on the right-hand side there is actually a summary of the aggregated tap-outs you see at different locations. So in that case, you see King's Cross, Oxford Circus, and Paddington, again, from 5 a.m. to 1 a.m. the next day. The top row is the ground truth. This is observable, but this comes from a synthetic model. This is still a synthetic model. And you see there that what is inferred from the two variations of the model, which are the blue and the red curves, does a decent job of reconstructing, again, the shape of these aggregated tap-out measures implied from fitting the model to the synthetic data. Okay? So there's some minor difference, like some peaks are slightly different in shape, but overall, since this is noisy data after all, that's, yes?
So are these like predictions or fits?
They're fits, right?
They are fits, like
On the left there.
Oh, no, here.
This is a prediction of the time.
so one step ahead.
No, we predicted the travel time of the whole journey.
But if I out of sample prediction or within the training sample?
I think it's in the training.
Okay, so this is a fit. This is fit here. But as you can see here, it shouldn't be, even out of sample wouldn't be a bad fit. And this is for travel time prediction. I almost say time travel every time. It's not time travel, it's travel time prediction.
This is what we want to do.
It's being recorded. This is just for the task of the travel time prediction using the actual real data. So again, the ground truth in this case is just observed is in the x-axis and the predictions are in the y-axis. This is out of sample, right?
Yeah.
This is out of sample. The closer to the diagonal line, the better the predictions are. And splitting here by size of station, by distance of travel. So these are the shorter travels, the medium-sized travels, and the longer travels. Sorry, the longer travels here, and this is the aggregate over everything. Again, it's showing, just as a baseline, just as to give you a sense of the magnitude, what a random guess would be. This is showing that in the upper row using these green points. It shows the magnitude of random guesses. And the bottom row here is the model that uses the first type of inference, which is the approximate model with a simple likelihood. Okay. This blue, let's ignore this blue, is kind of an initialization method that is based on the same model, but the optimization is done a bit differently. So there's a shortcut to fit the parameters of the model. That's what this blue guy does. So this is actually computation very cheap, but you can use maximum likelihood to refine that to get an improvement. So it's less visible what the improvement is, but there is an improvement of combining the simpler, crude way of fitting the parameters with the actual optimization or the likelihood function.
Could you explain, is it the first column and the last column are different travel lengths? Because they both look...
Yeah, so these are different strata, shorter, medium, and longer term. This is a combination of all.
Okay.
Yeah. Just to see whether different models have better behavior, different strata. Okay, finally, these are station loads estimation with the real data. And there, you don't have the ground truth because there's, at least with this data set that we have, there are only indirect measurements of loads. We don't have direct observation, how many people are at each location of the tube at each moment of the day. So there's a surrogate measure. The surrogate measure is the weight of the trains. For some particular lines, at the time the data was collected, there was actually scales in some trains. You could see the relative weight change in some particular segments of the tube. So what I have here, because the actual magnitude is not too easy to match, but you can see the relative difference between different times of the day. So rescale the shape of the function of these weight measurements to have a particular fixed area under the curve. Get a better sense on whether we're capturing that shape of the different loads as the time varies in the day.
So that's seconds past midnight.
What's that?
That's seconds past midnight, the axis.
The minutes past 5 a.m.
Past 5 a.m.
Yeah, these are in minutes. So at 5 a.m. to 1 a.m. the next day. Okay, so this typical 9 a.m. Peak and the typical around 5, 6 p.m. second peak. Okay, so under the surrogate measure, so of course our model that estimates choices of trajectories and time travels will imply estimates of loads. So the load estimates that are implied by the model are represented here in expectation. So you can see again, at least in terms of the shape, it's doing an okay job on reconstruct what the surrogate measures of load usage do. All right? So this basically ends this first problem that we presented here. The second half, which is actually work in progress, I can just tell you what I'm doing in case you want to hear more about it and come to me, is essentially an idea on understanding unplanned disruptions. So what happens on unplanned disruptions? We had a previous paper on this. So this previous paper would address questions such as, if you have a disruption between 2 points in the London Underground, what would happen to passenger behavior at some locations in this segment? So you could, for example, here Victoria and Brixton, the entire Victoria line was down. So you have some measure of passenger behavior, which is in this case was number of tap outs. It could be something else, but number of tap outs was the easiest to use here. And the whole idea was you have a history of natural regime days and no disruption takes place. You have some database of disruptions, things which are cataloged by TFL itself, saying this was closed from this to that. So you had that as part of the data. The idea is to understand, knowing that disruption takes place at a particular location at a particular time, what we'd expect to see in terms of passenger behavior. So we parameterize how the natural regime, so how what's the average number of tap-outs would be during that time, would relate to what actually happened during the disruption. So we observe several examples of that at different locations at different time. So we have a predictive model that has some few free parameters, which would learn how to map what would have happened if no disruption had taken place to what actually happened. So out of sample, when you want to understand how a different disruption would behave, we'll use this model to make projections on how different volumes of tap-outs would be different from the natural regime at these locations, given the place of disruption, given that time of disruption. So this is a problem set up. We had a previous paper on that. Here, working on some methodologically more sophisticated ways of doing that, like looking at the entire distribution of these numbers of the step-outs instead of just the average behavior. So I'm happy to discuss this offline because I don't think it's worthwhile to start it without going to the details of it. It's work in progress. It's much more theoretical than this previous paper, but hopefully something more interesting on top of what we did before in the past will emerge out of it. I'm happy to discuss this later on. Okay. Now, just want to thank the sponsors for it, and thank you very much for coming here today.